Hello, today I want to talk about how models are optimized for inference. So let's talk about DeepSeek. So typically when DeepSeek drops a model, they'll upload their model to Hugging Face. And they'll have a paper, they'll have a bunch of evals and stuff. And they'll also upload all their model weights as safe tensors. And then they're also going to upload a reference model. And this reference model is not optimized at all, but it's really readable. You just have these PyTorch NN modules, and it's great. But obviously this is not very optimized. So what happens after the reference model is uploaded is places like NVIDIA, places like vLLM start to get to work. So one of the common next steps is you do what's called quantization. And the basic idea behind quantization is that the weights oftentimes are going to be at a higher precision than necessary for inference. So for example, we might store the weights with 16 bits, but certain parts of the model, maybe you can store it in 4 bits or 8 bits. And so what places like NVIDIA do is they quantize these models. So they take these weights and then they quantize them into lower precision, and then they upload their own thing. So in this case, NVIDIA has this DeepSeek 3.2 NVFP4. And so now these model weights are quantized. Now, after you have this quantization, then you have to start optimizing the compute. And this is where places like vLLM and SGLang come in, where they will create optimized kernels and compute to be able to load these quantized weights and run them during inference. And so this is a pull request by Wusuk, who I'm not sure he was going to land this, but I thought it was like a pretty interesting pull request, and it kind of just represents how you productionize these models. So at a high level, they're just like various things. This is for piecewise CUDA graphs, which we might talk about in the future. This is for weight fusing, where oftentimes the format stored in these checkpoints might not necessarily be what you want to store in your actual weights of your model at runtime. In particular, you might want to fuse weights together. So code like this handles that. We do registration so that we can register, hey, for DeepSeek 3.2 and VFP4, we can use our model. And then we get to this. So going back to this diagram, the high level way to think about these models is you have a model, and models contain many layers, and within layers, they run kernels. And that actually maps really nicely to this, where you see kernels, layers, and models. And indeed, you see in the kernels, you have a bunch of Triton kernels that are defined. These Triton kernels actually compose. So you'll see that you have this get cosine sine, but then this get cosine sine is used within this fused norm rope kernel, and this might be used in another kernel, etc. These kernels are used within layers. So in particular, you can see that for this DSA layer, you end up calling various kernels that you define up there. And then the model is comprised of layers. So as you can see here, it initializes a bunch of DeepSeek V3.2 decoder layers, which was defined in the layer file. And then the forward is really beautiful, right? It's just like what we talked about in past lectures, where you get your inputs, you embed them, you run them through your n layers, and then you call your norm, and you're done. And for the actual model, we will project it to a particular token. Yeah, so I think that's at a high level. Oh, and then the last thing I want to talk about is MTP. So you'll notice that in this pull request, there's also this MTP file, and this stands for multi-token prediction. And this is used for speculative decoding. And so we're going to quickly just run through the intuition behind MTP and speculative decoding. So the high level idea is that typically you have your input and you predict your next token. But at this point in time, the model actually has quite a bit of information, and it can probably make a decent educated guess as to what the next token is. Maybe not at the accuracy of the next token, but a decent guess. And so the idea with MTP is that you're going to augment your model to have like this additional augmented head. And when you run through your model, you're going to predict the next token, but you're also going to speculate on the next token. So let's take an example here where we have the prompt 100 times 10. So as we know, the answer should be 1000. And on the left side, let's assume we have really good MTP. So in particular, it's super accurate, it always predicts the right token. And on the right side, let's assume that we have a really bad MTP. This is always wrong. And let's see what happens. So for good MTP, what's going to happen is the model is going to predict 1 for the next token, and the MTP is going to predict 0 for the next token. So in particular, it's going to predict 1, 0 for the next tokens. And what we're going to do is, for the next batch, we're actually going to run 100 times 10 equals 10 as the prompt and see what the model generates. Now, if you looked at past lectures, you'll know that when you run these inputs through the neural network, you can actually calculate batches, right? So in particular, you can see what the model would have predicted had it been only 100 times 10 equals 1. And you can also see what the model predicted had it been 100 times 10 equals 10. And so in this case, because the next token prediction for this is 0, which matches the next token prediction from the first batch, we can basically skip around, right? We can basically say, hey, okay, like this is actually correct. And so we can just use this 0 as the next one, and we can use this 0 as the next token. And so basically in the next batch, we can say, hey, 100 times 10 equals 1000, what's the next token? And they both predict end of sentence, and boom, we're done in 3 batches. Okay, so now, like, to understand deeply what's going on, let's talk about what happened when you have a bad MTP. So when you have a bad MTP, what's going to happen is it's going to be wrong, right? So we're going to say 100 times 10 equals 1 and 3. And we're going to feed this into the next batch. And the model is going to say, hey, wait a minute. For this prompt, I would have actually predicted 0. I would not have predicted 3. And so therefore, we have to throw this away. And our next prompt is going to be, it's going to be effectively this. And then we're going to use this bad MTP again and do 106. So again, like when this comes around, the model is going to make 2 predictions. It's going to make the predictions for what the next token would have been for this prompt and this prompt in parallel. And again, it's going to say, hey, no, like I disagree. You predicted 6, but I predicted 0. So we have to throw away the speculation. And then we do the next round. And the next round, we say, okay, 100 times 10 equals 100. And then speculate 9. Again, we compare what the model would have predicted at this point. And the model would have predicted 0, but the MTP was 9, so we have to throw it again. And then the last one, is you do it again, appending this 0 on and this 8 on. And you see that, again, the MTP was wrong. We should have predicted end of sentence. The model predicts end of seconds. And in this case, you don't actually have to do it one more time. You can just say, oh, the model predicted end of sentence. So this is clearly the answer. But as you can see, like this idea of speculation, especially if you have speculation that's like reasonable, can actually save you a lot in time. And so that's what MTP is. So yeah, hopefully this was interesting. I found it useful to go through this to build a high-level intuition on how these models go from completely unoptimized models and weights to pretty optimized inference-ready configurations. So yeah, see you in the next one.